Okay, so well, welcome back to class. I've had a pretty rough last couple days. I think we last met on Thursday, and on Thursday I actually was, at least during your class, I was feeling fine, but I had a night class, and then I started to feel a little ill during the night class, and so the next morning I tested myself for COVID, and tested positive. So I sent an announcement out. We had some family come in town. You guys know I take care of my mom. She's 80, but we had family come in town against my will, and I think they probably brought COVID to us. So, but I'm actually feeling okay. It's a little bit tired, a little annoyed, but it could always be a lot worse. So, um, what I want to do is we're going to finish up the semester. We'll actually only have today and then one more meeting. We won't have any more labs, as I said in the announcement. Um, a couple people text me. I've been putting grades into your Canvas. I had a couple people text me concerning grades. So let me just speak to that real quick. I have a couple documents, at least two, probably more, but at least two with no names on them. So I don't right now have a way to verify who they might belong to. I tried to match the writing, but I'm not very good at that. So I do have a let's see, I do have a experiment number two with no name. So if you got a zero for experiment number two and you handed it in, this could possibly be yours. So that was the one on Thevenin's theorem. I also have a multi-vibrator
Oh, that's
design
mine, I
practice
think.
build.
I think that's mine. I think I think
You
it's
guys hear
mine.
me?
Yeah. I think it's mine, the multi-vibrator one. I think.
I also think that lab number 2 might be mine if that was done on paper rather than the exam sheet.
Oh, we can't hear
Well,
you, I think.
can you hear me now?
Yeah, now I can hear
Okay, because I have some distortion. I don't know if you guys. All right, let's try this again. So I don't know if I cut out or at what point I cut out. But you guys, can everybody hear me now? If you can hear me, give me a thumbs up. There's a raise your hand. There's a thing you can raise your hand. Colin, all right, great. Okay. Okay, so I was saying that I have two documents. I have a Thevenin's theorem experiment two with no name, and I have a well, we did the multi-vibrator lab. I have one of those with no name. I think though what I'm going to do is for the multi-vibrator lab and the transistor lab, I kind of remember everyone being there. So even if I don't have a document for you, this could be yours. I'll go ahead and give you a grade for it. I think that that was more of a verification lab, so I'm pretty comfortable with. I don't know whose this is. I'll try to
you.
scan it or
I think it's
something.
mine, I think. It's mine, I think. Rishikesh,
Okay.
multi-vibrator one.
Well,
Yeah, yeah.
yeah, I don't know because I had two people that said they didn't get a grade for it. So what I'm going to try to do is scan these and see if we can ID these, and maybe I'll post these. Try to do it before the next class. So we'll figure it out. Um, the other thing is, well, right now I'm displaying the exam. Let me talk about that real quick. So overall, I think I was, in general, I was pretty happy with the exam results. I mean, we have some people on the low end that, of course. I wish that had done a little better, but I think overall people kind of knew what was going on. I was a little disappointed with I think one of the most missed problems on the exam, to my surprise, was locating the Q point, and that's just a series of steps, calculations that really not a whole lot of thinking there. But I guess I would be more worried if we had a in-class final and that was going to be a part of the final exam, but since your final is going to be a take-home, you always have access to your notes in your book. You can kind of look stuff up in there. But I think overall, you guys as a group did a decent job. If you're on the low end, I have 2 people below 60 and 3 people in the 60s, I mean, I would be a little bit concerned and want you to maybe, to kind of step it up, at least kind of understand what you might have done wrong. But I think, I think, I don't know. I think with the final being a take home, it's going to be a take home, and I've kind of tried to cover some of the information I'm going to ask, but some of it's you're going to have to look up. It's going to be what I call a research type of thing. So some of the things that we talked about in class will correspond directly to the final, and others it'll be related to what we talked about, but you have to do a little bit of digging. So even if you were in the group that didn't do as well on exam 2 as you would like, I think you can demonstrate that you still can get your mind wrapped around these topics by showing me you can do that on the final exam. And since it's take home, I think you should be able to do okay with that. And the other thing I want to say before we start is you might have noticed I posted the exam 3 project. I've been talking about it for weeks now. It is posted. So if you did not do well on exam 1 or well as you would like to have done, or you didn't do as well as you'd like to have done on exam 2, exam 3, that project, basically you're watching videos and you're going to summarize what you learned, or at least what the videos discussed, and I'm going to count that as an exam grade. So what I'm saying is you got a chance to really, if you didn't do as well as you wanted on one of the other exams, you got a chance to really, really help your grade out. So I would highly recommend, I would highly encourage you to get on that. Don't wait until the last minute, because remember, I'm going to post the final probably late Thursday or early Friday, and you'll have until Monday to do it. And you don't want to have to try to do the final exam and the exam 3 project that I have posted for you at the same time. So let me get into the lecture and the material, and then I'll take questions towards the end. And if you're one of the people that I get a text, I think I got 2 texts from people concerning grades and zeros, and we can discuss all that towards the end. So let me get into the lecture. And oh, before I do that, before I forget, I think what I want to try to do is to you guys, I know you have a lab to turn in on the Q Point lab from last week. I don't know how well that went. I think some people, the data was okay, but some people I felt a little frustration. So you have to just kind of turn in what you have on that, and I'll be lenient when I grade it. If we had met this week, today, we would have actually built the amplifier, but well, that's not going to happen. So I think what I'm going to do is I have a lot of stuff to return, so I'll probably go up to campus and just put this stuff in the box and then leave it in the room. I think that's what I want to just leave it in the room, and you guys can pick it up if you want it. If not, then we can discard it later. But I'll set it in our room in a box. You can just kind of get that. And then there was something else. The assignments you have to turn in. I know the lab. I'll try to make that uploadable. So if something you got to hand in, I'll try to make that uploadable. For the lab, I got to think what else you might have out there. I'm not really sure right now. So anyway, I've talked enough. Let me get into the lecture, and then I'll stick around after class to take any questions. Now, so I don't know how well, guys, you can see my board. I'm actually in the basement of my apartment building, and I got like a little corner, a light overhead. You can probably see the reflection on the board, so it's not the best situation, but I actually taught here for almost a year when COVID first hit, and we got kicked off campus. I put the walls up here and hung the board up, and I taught out of here for basically the whole year. And I didn't think I'd end up back here, but here I am. So it's not the best situation, but it's better than nothing. So I know I got a little glare up here, so I'll just try to do my best to write as big as I can and the right around the glare. And if anybody needs me to, move things around the board because you can't see because of the glare, just let me know. I do want you to text me. Go ahead and text me for attendance. The number is 513-494-6162. In that text, put your first and last name, and then put the class the class title, which is electronics. I'm going to use that for attendance. So go ahead and text me now, 513-494-6162. In the text, put your first name and last name, and put electronics for the class, and then just send that to me, and that'll be the way I take attendance today, and then on our final meeting on Thursday. So let's get into the topic that I want to discuss. Actually, a couple topics I want to discuss today. And as I said, it'll be a little bit of time after class, and we can talk if I need to talk to anybody. So in the last class, we kind of wrapped up the amplifiers, and we dealt with a class of electronic devices called thyristors. And I don't know if I mentioned that there's a whole class of devices. I know I only talked about or kind of mentioned briefly 3 of them. But there's a whole class of devices called thyristors. And I chose 3 of the ones I think are probably the ones you're most likely to come across. At least 2 of them are the ones you're most likely to come across. And definitely one of these is the most used thyristor of all. And the other is I just think it's interesting. Maybe a little outdated, but we'll talk about it. So the first thyristor is called a SCR. SCR stands for Silicon Control Rectifier. And then there's the triac, and then there's the UJT. UJT is a unijunction transistor. And that's the one that might be a little bit outdated. And I think we talked a little bit about the SCR. Of the 3, the SCR is the most important. Of the 3, the SCR is probably the one you're most likely to come across. Matter of fact, in the order that they're on the board is the likelihood that you will come across. Probably the most likely would be the SCR, and then the triac, and then the UJT. The first thing you want to know about each of these thyristors is that they are 4-layered devices. You remember we talked about we showed the block diagram of a diode. The diode was a 2-layer device. It had a P and an N side, P and an N, the P-N junction. So it had P material and N material fused together. And then we talked about 3-layer devices. That would be the transistor. We talked about the NPN, and we talked about the PNP. Well, the thyristor is actually 4-layer devices. They're 4-layer devices. And I believe I showed this in the last class, but I'll show it again. So the basic thyristor, and this is, this to represent the first one, the SCR. You have 4 layers. You have P material, N material, P material, and N material. So you have 4 layers. So you have several P-N junctions to deal with. So it's more complicated than the transistor. You also have an anode, and on the bottom a cathode. I don't know if you can see, I'm writing pretty low on the board. Typically, when they want to represent the anode, they use a capital A, and cathode, they don't use a C, they use a capital K, or I'm sorry, capital A and a K. And then, but there's a third lead here. There's a third one, and that's called the gate. And I want you to think of the gate as a trigger. Trigger. And you dealt with triggers before, because in one of the design problems, and in fact in one of the labs, we dealt with that famous IC chip, the 555 timer, the 555. And on that chip, that was one of those multi-vibrator circuits. You had an input. It wasn't called the gate. It was actually called the trigger, but basically it had the same effect. It was a way of starting something. In that case, a way of starting the timer, telling the timer when to go, when to time. And so you have the same thing here. You have this input. It's an input called the gate, and it's, just think of it as a trigger. And so this diagram here mainly applies to the SCR. We can extend it to the triac. It doesn't apply to the UJT. We'll get to that here shortly. But I want to focus right now on the SCR. And so I think I showed this in class. And I want to show that the symbol is basically, you can think of a diode, just a regular diode. But added to this diode is this other input they bring out. And this would be your anode. This would be your cathode. And this wire over here, that third one, is your gate. And so you have 3 connection points. You can see, and one important thing to remember is if I'm connected between the gate and the cathode, well, that's like being connected across this bottom PN junction right there. So, as you know, if that's forward bias, then the voltage across that is going to be 0.7 volts. So that actually turns out to be pretty important because one of the specifications that you would get from a data sheet for this device is called the gate trigger voltage. The gate trigger voltage. And that gate trigger voltage is one quantity I want you to remember. It's the minimum voltage that you have to apply across this junction right here in order to get this thing to turn on. So the way it works is like this. Actually, I want to show this, just kind of represent this a different way. It's going to function as a switch, and you might think to yourself, well, hold on a second, Singleton. Why can't we use just a regular transistor as a switch? Well, if you go back to when we first introduced this a couple days ago, the currents and voltages that this thing can control are huge. So there's no transistor this can actually control thousands of amps of currents and thousands of volts of electricity. So as far as a switch, this is a really useful way to turn something on and off, whether we're dealing with small voltages of current or really huge voltages of currents. But let me give you the actual circuit. And I'm going to come back to this diagram and a way to think about the way the circuit behaves. So you might have this, we'll just call that the load resistor. And then you'd have your device. And your power. And then you bring the trigger out. And what we need right here, in order to get this thing to fire, and actually what I want to do, let me put an output right here. So I'm going to put an output right here, and then this is going to be my V out. Between there and ground is going to be my V out. And the way this works is if this thing is off, that is, if I haven't triggered it, if this thing is off, then it's like an open switch. And so if I model that using an open switch, it looks like this. And I have this point coming off. If this is off, it's like an open switch. And if you think about it, if you put a voltmeter on the output, if I put a voltmeter on the output, put my voltmeter right here. If I connect my voltmeter between this output and ground, what do you think I would read? How many volts would I read? What should I expect to see?
VCC.
Say it again.
VCC.
I think that was Mr. Clark, but I think he got cut off. But this might have been a Maya question, because if this is open, right? If that's open, no current can flow through to ground, which means that resistor is not dropping any voltage, and if the resistor is not dropping any voltage, then I'm going to measure VCC. So with this thing not turned on, I actually have an output voltage. If I triggered this and I turn this on, so now the switch is closed, and you can see that basically my voltmeter is shorted out by the switch. So basically it's going to read 0. So it kind of works a little bit maybe the opposite of the way you think, because when I haven't engaged this, when I have not turned the circuit on, I haven't turned it on. And by the way, when you turn it on, the thing is locked on. We call it a latch. We say it's latched on. By disconnecting the voltage source from the gate or the trigger, it does not turn it off. The only way to turn it off is to decrease the current. But we'll get to that in a second. So I want you to just think of the point between here and here. Think of that as that switch that can either be open or closed. If I have not triggered this, then this thing is basically open. This is open. And if it's open, I'm going to measure VCC because no current can flow through the resistor. And no current through a resistor means I can't drop the voltage. I can't drop VCC. So I'm going to measure VCC between here and the ground. If I trigger this and this thing is actually on, then it's a closed switch, I'm going to read 0. So I can switch between VCC and 0 volts. Again, you can do the same thing with a transistor, but there's no way to switch 2,000 volts with a transistor. You can with this device. Now, I don't know if I mentioned this, but the SCR only works with DC. That's worth writing down. The SCR can work with DC. The triac can work with either AC or DC. You'll normally see this with AC. We'll get to that though. So back to this. There's some important parameters that you want to know to understand the operation of this. And one I've already mentioned. So I got my symbol back. Now, in order to trigger this, there's a voltage called the gate trigger voltage. There's actually two. There's the gate trigger voltage and there's the gate trigger current. And that gate trigger voltage is the minimum current needed to get this thing to turn on. The gate trigger current is the minimum current needed to get this thing to turn on. And when we turn it on, when we trigger it, remember it's latch. It doesn't, when I remove the signal from the gate, it does not turn the device off. You got to turn it off another way. So these two parameters here are data sheet parameters. When you buy an SCR, you can look up the value for VGT and for IGT. Those are standard sheet values, data sheet values, I'm sorry. So, of course, this is going to be really close to 0.7. We expect this to be close to 0.7. But often, the trigger voltage might be way greater than that. So what you want to do here is, normally what you'll do is you'll end up putting a resistor in series here with the gate. And then you might have your trigger voltage over here. So I'm going to call this VN. We'll call that RG. Okay, so if I had a situation like this where I was going to control it with a voltage higher than 0.7 or higher than VGT, then what I would have to have is my VN would have to be greater than, well, it's got to be greater than, well, I got the data sheet parameter, that VGT. So it's got to be greater than VGT. And I also have, so got two voltages here. If you think about it, I got that voltage VGT, which is going to be close to 0.7 because that's that forward bias diode. But if I have current flowing here, and I got to have the minimum current would be that IGT. That's the minimum current to turn this thing on. Then I actually have VGT and the voltage across that resistor. So it's going to be, that voltage drop is going to be this IGT times RG. So I think I have this formula on your handout. I didn't upload the handout to show it, but you have this because I passed it out in class. But this is one formula that you would need to figure out what's the minimum voltage I need if I want to get this thing to trigger. So write that down on something, or if you have the handout I gave in class, go ahead and you might want to highlight that. Now we mentioned how you turn it off. Once you trigger this, let's say I make this variable and I started it up 0 and I slowly turn this thing on, turn this thing up. And once I hit this value right here where my Vn is greater than VGT plus the voltage drop across RG, once I hit this, then this thing will turn on. And that is that the value across here, this thing will act like a closed switch. And if I were to back off of this or totally disconnect the VN, this thing is latched on. That does not turn it off. The only way to turn this off is there's an actual, what you got to do is you got to decrease the current flowing through the device. And there is a, you call it a hold current, IH. That hold current. And that hold current, as long as you're above the hold current, then the device is latched. And the only way to turn it off is to go below the hold current. Now, usually there's no way to directly control current, but you can control voltage. So usually what you want to do to turn it off is you just decrease VCC. So VCC, once you get below a certain value, it will cause the hold current to drop, and then this thing will unlatch. So I had an equation. Let me see if I can remember what it was. VCC would have to be less than 0.7 plus, you got this IH, that's the whole current, again, like VGT, and just like IGT, that's something you get from the data sheet. You can read that, that's a data sheet parameter. And the resistance that that current is going through is RL. So this formula right here would give you the minimum amount VCC would have to be in order to turn the thing off or to unlatch it. So with this device, there's really only two equations you have to concern yourself with. And it's those two. So this is to get the thing to turn on. This is to get the device to turn off. What else do I want to say about this? The beauty of this, I really am a big fan of SCRs. I think we discussed one of my favorite IC chips is the 555. We played around a little bit with that in lab. You did the multi-vibrator and the timer and all of that. But we want to know how, if I was designing something, how could I interface something big with the 555 chip so it could only source or sync 200 milliamps on the output, pin 3. Well, one way to do it would be to use a relay. We looked at relays, you watched a video on relays, and you can connect a relay to the 555 and use that to control any device, big or small, AC or DC. You can actually trigger this with the output of a 555. The only issue you would have is, remember, to turn it off, you got to do something. It's a little bit more complicated in that you can trigger this with a 555 and get this to drive or to control a really big, heavy load. But to turn it off, your circuitry would be a little bit more complex, but it's doable. So this is a really, I think of the thyristors, there's a whole slew of thyristors, and I've only put 3 on the board and talked about this one, but this will be the most important one. So expect to see some kind of basic problem on the final exam that has to do with this, but it's not a whole lot here. So I want to do a practice problem, and that's just practicing using these equations. That's really all it is. Does anybody have any questions for me on the thyristor, the SCR thyristor, before I go on to the next one? Any question on the SCR? Okay, so there's a couple things I want you to remember now. The one thing is this is DC only. Don't forget that. SCRs can only control DC. The second thing is it works as a latch. It means that once you turn it on with the trigger or the gate, by removing the signal from the gate, does not turn it off. It's latched on. Latch means locked. And the only way to turn this thing off is to decrease the current flowing through the device below that whole current. And most of the time you can't control current directly. You control current by controlling voltage. So basically that translates to I got to decrease VCC until that whole current drops below whatever this value is, and then the thing will unlatch and turn off. So those are the key concepts I want you to remember for this particular thyristor. And of course the symbol, know the symbol for it. Now it's really not a whole lot you can mess up with on the final exam because it's a take-home exam. You can always look the stuff up, but still, I mean, you want to have this stuff at your fingertips. So if you have the handout, I didn't upload it. I didn't upload it to the video thing here. But if you have that handout that I had in class, go ahead and take that out because there's a practice problem. There's actually 2 on the bottom of the sheet. I thought I had 3 practice problems on here. I don't know if I had 2 pages or not, but I guess I just had the 2. But these are the 2 most important ones, so it doesn't matter. So go ahead and get this sheet out from last class. It's titled Thyristors. And there's 2 practice problems at the bottom of the page. Go ahead and sketch up the circuit. Or just grab a sheet of paper, sketch up the circuit, put in the values, and it's just using these equations. And let me know what your values are. So I'll give you a few minutes to do that. And I'll clean the board up. All right. So there's a circuit. This could actually be your load. I might have maybe I have a motor here or I have something I'm switching. Now, before I drew the output here, and I was measuring between the output and ground because I just wanted basically either have an output voltage or no output voltage. But if you're actually controlling the load, you don't need this wire. It all depends on what you're doing. So this could be any device you want to control. But you have the circuit, your current limiting resistors, 1K, low resistor, we're switching is 100 ohms. But this right here is what you get from the data sheet. Every data sheet for an SCR will give you this. This is the minimum information that you would need and that you can get from the data sheet. And so you would just basically plop these over here into this equation. I don't have the room to do it here, but you can go ahead and put in a 0.75 for VGT, the 7 milliamps, and this is 1K. Let me know how much voltage do I need to get this thing to trigger, to turn on? Anybody do the calculation?
I got 7.75 volts.
How much?
I got 7.75 volts for VN.
You're breaking. I don't know who that. Somebody's trying to give me an answer, but you're breaking up. Can you guys just?
Hello?
Yeah, I can
I
hear you
got
now.
7.75 volts.
Okay, 7.75 volts. So this is the minimum voltage, 7.75 volts, to get this thing to fire. And then if you were to decrease that, then this thing's staying on, it's latched on. And so the only other way to turn it off would be, gotta drop the current, gotta let me less than this 6 milliamps. That's the whole current. 6 milliamps and above, it's gonna stay on. Go below the whole current, it'll unlatch. We do that by decreasing the voltage. And so that's this other equation. This is my one equation. Anybody calculate the minimum VCC required to turn it off? What would that be?
I got
We are out.
1.3 volts. I got 1.3.
1.3.
Yeah.
Anybody second that?
Yeah, I got that as
Anybody else
well.
get 1.3? Okay. All right. So like I said, there's not a whole lot here. With just two equations, anything I would ask about or expect you to understand, mainly conceptual, the concepts of what I just went through. I spent we can do the equations in 2 minutes, but the concepts, I want to make sure you understand what's going on. And the big thing is that this thing functions as a latch. So that's pretty much it for this. Anybody have any comments or questions on the SCR? Very, very, very handy device. Okay, so you want to remember DC only. Now the other one, the triac, I'm actually not going to. I just want to show. I think I've already showed you the symbol for this. We'll just talk about the concept. So the triac, think of it as a AC. Think of it as an SCR designed for AC. The triac actually, you can think of the triac like this. First of all, the symbol's a little complicated. It looks kind of like this. It's a little hard to draw. These lines don't go exactly like that, but it depends on whose book you pick up. So this is the triac. And you'll probably get a better picture in your book. They're trying to show you that you have two diodes in parallel, reversed. And what I mean by that is, you can think of this as like this. A diode like this, in parallel, a diode like that. And then you got your trigger circuit. So you got a D1 and a D2. And the way this works is only one diode is on at a time when you trigger it. So if you, here's your load, here's whatever your load is here. Now this is an AC load. So if you got AC across here. So if you have AC across there, then what you'll have is you have, if you think about your first diode approximation, a 4 bias diode is like a short circuit. So when the polarity is like this, basically D1 is a short, D2 is an open. And so your AC current can flow through. When your AC reverses, you have the opposite picture. Now you have this is reverse bias, so it's an open. And this is forward bias, so it's a short. And now your AC can flow the other way. So it's this SCR kind of, but designed to have current flow in two directions. Again, you can use this to control AC devices. If you use a SCR with AC, then basically what you have is a rectifier, because it's going to, remember, a SCR is still a diode. Even the symbol looks like a diode. So if you try to control AC with this, it's going to look like a half-wave rectified signal. So you got to have a conductive path for both sides of the AC sine wave cycle. So I think really all I want you to know about that one is the name, know what a triac is, know that it's designed mainly for AC. You can use it for, I don't know what you would do much with it with DC, but mainly AC for this one. And it says description and symbols, what I have on my sheet. So there's a symbol, there's a description. Just kind of conceptually how it works is what you want to understand for this one. Anybody have any questions for me on the triac? Okay, if you go back and review this, spend most of your time looking at the SCR, maybe a little less time looking at this, and the last thing I'm going to talk about is called a unijunction transistor. Used to be one of my favorite transistors when I was in school, but they since come out with other things to replace it. Don't spend a whole lot of time on that. I mean, just know what it is, and the SCR is the biggie. So the third thyristor I want to talk about, third and final one, is the UJT. And that stands for unijunction transistor. Now, why they call it a unijunction transistor? Well, you know, we looked at transistors, and they're three-layer devices, right? There's a junction here, and there's a junction here. With this transistor, what they have is they have this this N material, and then they have some P material right here. This is P material. They have a connection here, and a connection here, and they have a connection there. This is the UJT. And what happens is basically this thing is, well, you have to, you know, you would have some kind of load here. I'm just going to draw it like this for now. So you would have that, not really biased, but you'd have some kind of load across here. But when this voltage, I forget the name of the voltage, standoff voltage, I think it's called. I haven't used this in years, so it's not like something I carry around with me. Yeah, the standoff voltage. When you hook up a device here, say we'll put up a variable supply here. Another datasheet parameter is called the standoff voltage, and that's unique to the unijunction transistor. So when you turn this up and it reaches whatever that standoff voltage is for that particular device, then this thing will actually conduct. Often what I see over here, again, they have other things that can do this now, but often what I see over here is a capacitor. I mean, you can put an RC circuit over here. Then we do like an RC circuit, and you got a timer. You can use this to make an oscillator. So I don't know. I'm probably not going to ask much about the UJT. Just kind of know what the letters mean. And again, this is kind of outdated. I mean, I guess I'm putting it up here because when I saw this, I was in college many, many moons ago. I could think of a whole lot of things to do this, and this is kind of outdated now. So, but if you're interested in the way this works, maybe to make something like a simple oscillator, then you can look that up in your book. So for this one, just kind of know what a unijunction transistor is. Probably by the time you get to be my age, this won't even be a device anymore. So I think I'm done with this. So just to sum up, we talked about thyristors. They're a class of four-layer devices, a lot used for switching. The most prominent one, the one I want you to remember, the one you'll be most likely to come across, is called a silicon control rectifier, SCR. We did a couple really basic practice problems, so I mean that's nothing earth-shaking about the math we did, but the concepts of how it works is what I want you to remember. You want to know that is DC only, and then the second thing, of course, the symbol. And then the second thyristor would be the triad. We didn't really do a lot with it, but I just wanted you to kind of conceptually to see how the triad works. Not a whole lot of math there. You really got to know what you're trying to do before you match the math to the problem with the triad. So they use that for to switch AC devices on or off, for speed control, control the phase and speed of motors. So there's a lot of applications with SCRs and triads and so forth. So if nobody has any questions, I'm going to move on to the final topic of the semester. Now, I think I mentioned to you guys, how much time? Yeah, I got time. That when Dr. Rabi asked me to teach the course in the summer, I said, well, okay, I know what electronics is, but it used to be electronics and then integrated circuits. In other words, this course would have been almost 2 semesters. So now it's just 1 semester within this new way of teaching or whatever. I don't know what they're doing. All the schools are doing the same thing in Ohio. So, this would have been just the beginning, and you'd had a whole nother course of this. And op amps, which is what we're going to talk about next, could have taken up most of that second course. So I was faced with what do I take out of the course? So I was really, I wasn't even going to talk about op amps because it could actually be a course in itself. But then I said, well, I don't know if I'm going to get any op amps, so let me at least talk a little bit about it. And so I struggled with this, how much of what to give you, because I don't know. I just think that that's an important device. So just so you've heard of it and you kind of know some of the concepts, let's talk about the operational amplifier. The operational amplifier. So they call the operational amplifier, or op amp for short. Now, I did not make a handout. Actually, I did make one handout. I'll put it on the screen here in just a second. And by the way, when I show that, I saw a little message here that you can actually download the documents from this application I'm using. So I didn't get a chance to post this document I'm going to show to your Canvas, but you can just hit the little button at the top when I show it, and you can download the document if you want. You can download the document I'm going to show. So what is an operational amplifier? Well, the name kind of gives it away, because back before basically integrated circuits, IC chips and transistors, they built linear amplifiers that could do math operations. They can do summing. You can do a summing amp. They can multiply. They can divide. They can do integration from calculus, and they can do differentiation from calculus. And so these amps are actually named after the fact that you can do math operations with them. And so over time, they kind of chopped the name off and called it an op amp, but it's short for operational amplifier. So that's the name, the meaning of the name. The op amp is interesting. It's actually an integrated circuit amplifier. The whole amp is on one piece of silicon, it's a complicated device. It's not like a simple diode or transistor, even the thyristors we just talked about with 4 layers. There's a lot, and I'll show you a schematic of what's inside of one of these devices. There's a lot of transistors, a lot of resistors, a lot of little microscopic devices that are, I think, pretty amazing. So let's look at the kind of the block diagram of an operational amplifier. And it's way more complicated now than the other devices we talked about because it's an integrated circuit. But we can kind of narrow it down to 3 main pieces. We'll call them stages. So basically, an op amp is it's made up of smaller amplifiers. And so the first small amplifier is called a diff amp. A diff amp. So write this down because again, I didn't make a sheet for you. So this amplifier is called a diff amp. Now I don't have the space to write it on my board. You write it. This diff amp, it's called a diff amp, but diff stands for differential amplifier. Diff amp means differential amplifier, and it's always the first stage of the op amp. It's the first amplifier. And then you have, we'll just say more amps or more gain. Let's say more gain. So you got another amp, or you can have even more than one. But you got these other amplifiers that they kind of hook them in series. They call it cascading them. They cascade these amplifiers, and we already mentioned why you want to do that. Because when you do that, you can increase the gain, the voltage gain or power gain. And so you got the diff amp, that's always the front end of the op amp, and then you got more stages of gain. And then this one you'll be familiar with. This is an emitter follower. Emitter follower. And that's that last amp we talked about when we were in class, the CC amp. That was the amplifier that it doesn't amplify. It had an AV, had a voltage gain of 1. And why would you want a voltage gain of 1? Well, because we weren't interested in the amplifying properties of that amplifier. What we wanted to do was, at least in the application when we were talking about it, is you remember that CE amp, when you hook up a low ohmic value load, if you're driving a speaker, that low ohmic value load can give what we call, can overload the amplifier, cause gain depreciation. So how do we fix that? Well, we took this special amplifier, that CC amp, the emitter follower, because it had a very high input impedance and a low output impedance. And so we can use the high input impedance, connect that to our CE amp so we don't load the CE amp down. But then we can use a low output impedance to drive a speaker, another low impedance device like a speaker. So it kind of worked out. This is the same type of thing, but this emitter follower is called a Class B. Class B, and it's called a push-pull amp. Push-pull amp. And a push-pull amp basically is an amplifier that it uses both an NPN and a PNP together, and it's biased a special kind of way. And the classes of this, we don't really have time to get into a Class B, the different classes, but you can look it up in your book if you want to know more about it. So pretty much, not every, but pretty much most every op amp is going to have these 3 stages. And what they do is they put all this in one box, and they call it a differential amplifier, or they call it an operational amplifier. Now, the other thing that's important to remember is over here, this diff amp actually has inputs. And over here, this emitter follower, it has 2 outputs, but usually we take one of these outputs and we'll tie it to ground like that. So we usually have this one output right here. This is called a single ended output, just one output. And over here we have a differential input, which means we have 2 inputs. We got 2 inputs and 1 output. So that's already something strange about this amplifier. So this diagram here, go ahead and write it down on something. And you should know at least these basic pieces, the basic parts. Now, let me show you the actual symbol, because that's going to say a lot. And then I'm going to show you what's really inside of this thing. I'll project that in just a second. But you want to remember that the front end, the very input side of the op amp, is a diff amp, a differential amplifier, and then the output is it's an emitter follower. And remember, we don't know much about diff amps yet. We'll talk about diff amps, but you do know about emitter followers, because this is the last one, the last amplifier we talked about. They have a very high input impedance, they have a low gain. We get our gain here. We don't want the gain here because that can cause distortion. We get the gain here. This doesn't add any more gain, but what it does add is a low output impedance and a high input impedance. So that's the purpose of it. So we got our diff amp. We'll talk about that, what that does. We got our more gain, and then we got our emitter follower. So kind of take a mental snapshot of this, write it down. I want to erase the board, and then I want to talk about the diff amp. Before I do that, let me actually show you what the inside of this thing looks like. Let me see if I can display it. I think I got it on my desktop here. Actually, I might have already uploaded it. Did I upload it already? This system I'm using is on this Collaborate. It's just so slow. And I thought it was because I had a wireless connection. Actually ran a hard wire from my router down to this machine so that I would speed it up, but that doesn't really seem to be speeding it up too much. So I don't want to wait. This thing the wheel is just spinning. I really want. What I'll do is maybe I'll put this on your canvas. Let me see. I'll put it on your canvas and you can get it from there. I just wanted to say something about it. Let me give it another try. I thought I uploaded this before class. All right, I'm not gonna waste any more time with it. I'm just gonna. Oh wait a minute, here it is. It just popped up as I was about to sign off of it. It just popped up. So now when this thing displays in the upper left-hand corner, there's a magnifying glass. You can actually zoom in. Go ahead and zoom in on this. There's a magnifier with a plus sign on it. You can zoom in on it. Blow that up on your screen, and just take a look at this. So this is an op amp called the 741. The 741 is a general purpose operational amplifier, and it's probably the most common op amp. It's like the 555. Two of the most famous integrated circuits on the planet. One would be the 555. The other one is this 741 operational amplifier. It's a general purpose op amp. But the reason I just wanted to display it so you can see. Look at this thing. It only has 8 pins. It's small. It's about the size of it's the exact size of a 555 IC chip. But look at all these transistors they have on the inside of it. And you'll recognize. We'll talk about over here where it talks about. Let me see if I can mark on this thing. I think I can mark. So over here. This is an input, the non-inverting input, and then right here, these transistors. Remember I said on the front end of this, you have 2 inputs. Well, one of those is called the non-inverting input, and the other is called the inverting input. So there they are. And this whole thing right here, this whole piece right here, makes up the differential amplifier. All of this is the diff amp. Now they have these, like the term offset, they have these things highlighted here. We'll talk about some of this here in just a second. Now, you don't really have to understand anything here. That wasn't my purpose of making this. I just wanted you to see how complex this is. I mean, you think about on a piece of silicon, the simplest thing we talked about was a diode. And then we went to a transistor, which is a 3-layered device, 2 back-to-back diodes. And then we learned about the thyristors. Now we're going to have 4-layer devices. But look at this. This is a device so complicated. You have many, many transistors and resistors all on a tiny piece of silicon. Pretty amazing. At the bottom of the sheet, if you scroll up, this is the pinout for the 741 operational amplifier. And so on one device, you have one amplifier. And, you know, we're not going to do anything in lab with this, but if you ever have to use one of these, of course, your inputs, so pin 2 and 3 and 6, those are the most important ones. So I'm going to switch to the camera because I want to, no, I just undid that. So I'm going back to my camera. I almost hate to go away from this. I don't know how long it'll take to get back. And I want to clean this off because I want to talk about the symbol for the operational amplifier. So just kind of remember what I'm erasing now. And there's 2 symbols to remember for this. So the op amp, all amplifiers are like that, they're triangles. But with the op amp, you have 2 inputs. And you have 1 output. So one of these inputs, they'll put a plus sign on it, and the other they'll put a minus sign. Now, you probably saw that on the document I just displayed to you. This is not plus and minus polarity. The plus means it's the non-inverting input. So non-inverting. This is the non-inverting input, and the minus sign represents the inverting input. So the plus and minus, that's the only significance, is that one is inverting, the other is non-inverting. Well, what does that mean? Well, what that means is that if you put an AC signal on this input, I put in this signal, what I'll get out is a bigger version of it. If you put in that same on this input, what you get out is a bigger version of it, but it'll be inverted. Okay, so that's one thing. This is weird. It's different. It's a different device because normally we deal with 1 input, 1 output. But this has 2 inputs because the front end is a diff amp. You got to have 2 inputs. So you can put a signal in here, get a amplified version of it, put a signal on inverting, you get a amplified version, but it's inverted. Another thing you can do is you can put this thing has the ability to actually take the difference between these. So what it will do is, let's just call this V1. We'll call this V2. What this will do, now you remember when we talked about your CE amp, we did a calculation when we took the output voltage over the input voltage. We actually did that. Remember we did the pi model, and we got the output voltage, we got the input voltage. And when we divide that, we got something called the voltage gain. Well, you can write this, you can say the output voltage is going to be the voltage gain times the input voltage. All amplifiers pretty much obey this equation, or one like this, except for the CC amp, because again, it doesn't amplify. So this is just a general equation for amplification. Voltage gain times input voltage is my output voltage for any old amplifier. Well, this amplifier, you can actually inject the signal into both inputs, And that's where the diff amp part of this comes in, because what it will do, my output is actually going to equal my voltage gain times the difference between the voltages on the inputs. So if I were going to use this and we'll talk more about this on Thursday, but you can use this in different modes. You can use it in single-ended mode, which means I'm only putting the signal in either the inverting or non-inverting. I'm just using one of these inputs at a time. Or I can use it in the differential mode, which means I'm going to inject two signals in, and then my outputs, instead of just being the voltage, input voltage times the voltage gain, is going to be the difference between those two. You can actually amplify DC with this. So if I actually put on this amplifier, if I put a voltage here of 3 volts and a voltage here of 5 volts, then what this will do is it'll take 5 volts minus 3 volts. It'll take that, and then it'll multiply that by whatever my voltage gain is. Now you're probably thinking to yourself, or you should be thinking to yourself, well, why in the heck would you want to do that? Well, actually, this is a good thing. I'll explain more about it later. Well, not later, it has to be Thursday, but I'll explain the importance of this. Because normally, you use this kind of in a double mode kind of way. You want to amplify a signal, but this has the ability to reject other signals. And so we'll talk about something called the common mode. And I don't want to go into the details of that. For number one, I don't have time, and number two, I don't want to overload you with information because it gets kind of detailed. But I do want you to know this. Now, the other thing I want to show you, I got kind of off track here, is that the other thing that's weird about this amplifier is it has 2 power sources. Normally we used to just one VCC. This amplifier actually has your inputs, your output, but you have a VCC, and then down here you have a minus VEE. Now you've seen that before. Some of you didn't like that. Excuse me. Excuse me 1 second. I gotta get something to drink. Oh man, I thought I muted myself. I hope you guys didn't hear all that hacking. I tried to go away from the camera, so sorry about that. But this disease is terrible. What was I saying? So you have a positive VCC and you have a negative. You've seen this in that last lab we did. One of the biasing schemes actually used a negative VEE. Now, why do we have a negative VEE? Why do we have 2? Well, remember the last stage I showed you on the block diagram? That last stage was the emitter follower, but it was a class B push-pull. And that push-pull amplifier, what it is an amplifier that uses both an NPN transistor together with a PNP transistor, and it's biased in a way. Normally when we bias it, we set that Q point right in the middle of the load line. But with that class B, with that push-pull, we're going to bias it in their cutoff. And it's a little complicated. We don't have time to go into it, unfortunately, but because of that last stage, that push-pull amplifier, you got to have 2 supplies. if you want to know more about that, just look in your book under push-pull amplifier, and then you can you'll be able, enough to be able to read and kind of get a basic understanding of the push-pull amplifier. So I'm running out of time here. Let me do one more thing. We'll kind of pick up with this next time. The way to think about this, so normally they don't show these leads right here. You just realize that they're there. But I want you, as a takeaway for today, to think about this like this. We'll start with this next class. The model for this is going to be, I got my amplifier. And what I want you to do is think about that front end, which is the diff amp. So you got I got my non-inverting input and my inverting input. And this right here is going to be my ZN. That's my impedance looking in this way. It's my eyeball looking in that way. And then over here, I'm going to have, how do I want to do this? I'm going to show a little AC source like that. And this is going to be my out. And this right here is going to be my Z out. That little circle there, little AC, is going to represent my voltage gain. I'll put a little AL there. I'll tell you what the AL means next time. Okay, so this is going to be our model for this. And ideally, if we could build a perfect op amp, we would have a voltage gain of infinity. We have a Z of infinity, and we have a Z out of 0. These are ideal. So write this model down, and probably want to show this grounded. Write this model down, and we'll pick up with this next class. We'll come back to this. But if I could build a perfect operational amplifier, this is how I want it to behave. There's more associated with this. I mean, there's other ideal parameters. I may type up some and put it on your canvas, but these are the big three right here. So I'm out of time. I wanted to save a minute just in case somebody had questions. So I'm going to stop this here. I did record this, so if anybody needs this to see anything else here, replay it, let me know. I'll put it on YouTube. I won't do it unless you send me a text. If you send me a text, I'll put it on YouTube, and you can watch this over if you need to. So let me stop now. Does anybody have any questions over on the material that we talked about? Any questions on the material? On the second part of my lecture today, which was on op amps. Any questions on op amps? Okay. All right. So now, anybody have any other questions? I know some of you, I texted one person about grades, zeros. I don't know. I think I covered the way the rest of the semester is going to go. Anybody have any other questions for me before we sign off?
I just had a question
Is
about.
anybody still out there?
Can you hear me?
No, I guess I don't think people are still out here. Okay, well, you guys are an easy crowd. Okay, well, I will say this. I'm going to, since I can't do anything else but sit here and what's the word I want to use? So I'll get the rest of the grading done. So it's a possibility that if you submitted some work and got a 0 for it, that it could just be out of order. If you didn't submit it with the rest of the class and I hadn't got to it yet, you may have a 0 in for that. If there's something you did not submit, if you're still holding on the papers, the lab, I'll make that uploadable. There's some other stuff you didn't submit. You may want to get a hold to me, and we'll figure out. I don't know. I may have a Dropbox or something to put this stuff in. I just got to figure out how to do it, but we'll handle more about that next class. I will be monitoring my texts if you want to text me, but I can't text back right away because it seems like the second I put a grade up, I get both UC and Cincinnati State people start to text me, and that means I can't do my work. So I got to get this grading done for all these classes. So just if you have a question, send me a text. Be patient. Eventually, I'll respond to it. And other than that, this is it for today. You guys have a great rest of the day. And I will see you for our last and final class on Thursday. See you later.